Hello students, welcome to this lecture on Kalman filter. Let us recall, we discussed the problem of signal estimation from noisy data through optimum linear filters. So, this was the problem. Xn is the original signal and it is contaminated by additive noise, we assumed white noise, and the resulting observation is yn, and when we filtered by optimal linear filter, we get the estimate of the signal x at n. FIR and IIR winner filters were developed on the basis of the WSS assumption of the signal. We assume that xn and yn are jointly WSS, and on the basis of that FIR and IIR winner filters were developed. The linear prediction filter illustrated an excellent application of FIR winner filters. We discussed the linear prediction problem, then linear prediction and prediction error filters, a faster algorithm for their implementation, and one efficient realization of the linear prediction error filter. The adaptive filters were developed to tackle non-stationarity in the data. They use a desired reference signal, Dn we call it, and update the filter coefficients according to the error between the filter output and the desired signal. The LMS adaptive filter is based on minimizing the instantaneous square error square n, while the RLS algorithm minimizes the sum of the weighted square error due to the current and past data. The Kalman filter provides an efficient solution to the signal estimation problem. This lecture will discuss the basics of a simple Kalman filter, that is the scalar Kalman filter. First, we will give a very brief history. Kalman filter was invented in 1960 by R.E. Kalman. Its origin can be traced to Carl Friedrich Gauss's least squares method. So, we discussed about this method in an earlier lecture. It was first derived as a discrete filter. Kalman and Bussy extended the filter to the continuous version in 1961. This is the version commonly used in control systems engineering. Kalman filter is widely used in statistical signal processing. Here is the photograph of R.E. Kalman. He was one of the best control theorists. Many of the modern control concepts like state space representation, state estimators, observability, etc. are associated with him. Let us again see the signal estimation problem. We have this original signal xn and this is the noisy signal, and after optimum linear filtering we will get the estimate of the signal. To estimate the signal xn in the presence of noise, FIR winner filter assumes a fixed filter length. So, in the case of FIR winner filter, the filter length is fixed. IIR winner filter is based on the assumption that an infinite length of data sequence is available, because it is infinite impulse response IIR. So, that way it makes the assumption that an infinite length of data is available. Neither of the above filters represent the physical situation, because data is neither infinite nor it is of fixed length. We need a filter that adds a tab with each addition of data. So, a new sample comes, then filter length will be updated by 1. The Kalman filter provides an efficient solution to this problem. So, such a filter is based on recursive estimation. In order to use the previous data, the filter length should increase with each data. Kalman avoids this by recursively implementing the filter. So, the filter is recursively implemented. Current estimate is obtained as a linear combination of the previously estimated signal and the current observation by the following relationship. We will see how this relationship is obtained. X hat n is equal to a n times x hat n minus 1 plus k n into y n. The Kalman filter is also based on the innovation representation of the WSS signal. We use this model to develop the causal IIR winner filter. Here also that innovation representation of WSS signal will be used. First we will discuss the signal model. The simplest Kalman filter uses the first order AR autoregressive or Markov signal model. Xn is equal to a times x n minus 1 plus Wn, where a is a constant and Wn is a white noise. So, Wn is a white noise, a is a constant. To tackle non-stationarity in data, a time varying AR parameter an is considered. We can use this coefficient to be time varying, so that non-stationarity of the data can be tackled. Like in the case of winner filter, Xn is assumed to be of 0 mean. So, that in all our signal estimation case, we assume the signal to be of 0 mean. The observed data is given by Yn is equal to Xn plus Vn, where Vn is another white noise independent of Xn and Wn. So, this is the measurement noise actually. This noise is independent of either Xn or Wn here. The vector Kalman filter uses a state space model. Instead of this simple model, Xn is equal to Axn minus 1 plus Wn and Yn is equal to Xn plus Vn. Vector Kalman filter uses a state space model. Recall that a WSS signal is modeled by a difference equation representing the ARMA PQ model. Such a signal can be modeled by the state space model and is described in terms of first order difference equation. Suppose in ARMA PQ it was a pth order difference equation, now it will be converted into a first order difference equation in terms of matrices. So, this is the Xn vector is equal to a times Xn minus 1 vector plus b times Wn. So, this is the state space model. The observations also can be represented as a linear combination of the states and the observation noise or measurement noise. That way Yn we can write as C transpose Xn in plus Vn, where C is equal to 1 0 0 transpose. So, it is a vector comprising of first element 1, rest of the element 0. Equations 1 and 2 have direct relations with the state space model in the control system, where you have to estimate the unobservable states of the system through an observer that performs well against noise. So, there also Kalman filter comes. We will consider one example. Consider the ARP model. So, here Xn is equal to A1 times Xn minus 1 plus A2 times Xn minus 2 plus up to AP times Xn minus P plus Wn. So, this is the pth order autoregressive model, where Wn is the white noise. because it is a pth order difference equation, there will be p state variables and we will take suppose x1 n, that first state variable, as xn. Similarly, x2n is equal to x of n minus 1, like that xpn, that is the pth state variable, is x of n minus p plus 1. If we assume these state variables, then this equation xn is equal to a1 x n minus 1 plus a2 into x n minus 2, like up to ap into x of n minus p plus wn. This relationship we can write as this x1n, that is the first state, is equal to a1 times x1 of n minus 1, because x1n is equal to xn, plus a2 times x2 of n minus 1, where x2n is nothing but x of n minus 1. So, that way this will be x2 of n minus 1. Similarly, the last term we can write as ap into xp n minus 1 plus this wn. So, this way the first state equation can be written in terms of other states like this, and here we see that all are first order difference. And according to the definition, x2n is equal to x1 of n minus 1, like that up to xp of n is equal to xp minus 1 n minus 1. So, that way all these state variables are represented as a first order difference form. So, this we can write in a matrix xn, that is the state vector comprising of x1n, x2n up to xpn. So, this can be written as xn is equal to a times xn minus 1 plus b times wn, where a will be now first row will be a1, a2 up to ap, and next row will be 1, 0, 0, next will be 0, 1 up to 0, like that, and last row will be 0, 0, last element 1. And similarly, b can be written as 1, 0, 0 up to 0 transpose of this vector. So, that way this is the b vector. So, that way we can write now xn is equal to a times x of n minus 1 plus b times wn, where b is a column vector with first element as 1, because there is only one wn terms in the ARP model. And similarly, a matrix will be given by this, first row will be given by the, that is first state, which is expressed as the linear combination of all other states, and where a1, a2 up to ap are the coefficients. And similarly, from the other representation of the states, that is x of 2n is equal to x1 of n minus 1, like that. So, this relationship we are writing by giving 1 in the corresponding position. So, that way this is the A matrix and this is the B matrix. This type of model will be used in vector Kalman filter, but first we will discuss the scalar Kalman filter. The Kalman filter uses all the available data. That way, let x hat n given n, this is the notation we will be using to denote the estimator. So, this means that x hat n given n means this estimator is based on observation till time n. So, let x hat n given n denote the LMSC, linear minimum mean square error estimator of x n based on the data y0, y1 up to yn. So, this is the estimator. Thus, x hat n given n is E hat x n given y0, y1 up to yn, where this symbol E hat is the linear minimum mean square error estimator. Normally, E of x n given y0, y1 up to yn, that is the conditional expectation, but since we are using the linear minimum mean square error estimation, therefore, E hat denote the LMMSE operator. Thus, x at n given n is E hat x n given y0, y1 up to yn. So, where E hat is the LMMSE operator. To denote linear minimum mean square error operation, we have used E hat. And if suppose signals are Gaussian, then E hat will be equal to simply E, that is the conditional expectation. The Kalman filter also uses the innovation representation of the stationary signal as in the IIR winner filter. So, we will derive the Kalman filter on the basis of innovation representation, but other derivation of Kalman filters are also available. However, the Kalman's method for innovation generation is not through spectral factorization. We know that in IIR winner filter we got the innovation process through spectral factorization, but here the approach is different. The innovation representation is shown in the following diagram, this diagram. A linear predictor can be used to generate the innovation sequence from yn. Here this innovation generation process is a linear predictor. So, this side yn is the input and y tilde n is the innovation sequence. This is the innovation process. Let y hat n given n minus 1 be the linear prediction of yn based on all past data, that is y0, y1 up to yn minus 1. Clearly, y hat n given n minus 1 is equal to, that is LMMSE estimation of yn given y0, y1 up to yn minus 1. Now, this yn we can write as xn plus vn. Therefore, this expression will be equal to E cap of xn plus vn given y0, y1 up to yn minus 1. This linear estimation of noise, because it is uncorrelated, given the data will be 0. Therefore, this will be simply the linear prediction of xn given data up to n minus 1. So, this is one important relationship. Therefore, y cap n given data up to n minus 1 is equal to x hat or x cap n given n minus 1. So, this relationship is important for us. Now, we can further write because xn is a times xn minus 1 plus wn and this vn is vn only. So, that way this will be x e cap of a times x of n minus 1 plus wn plus vn given data y0, y1 up to yn minus 1. And this quantity is the estimators for x of n minus 1. So, that way given all data up to yn minus 1, we are determining x of n minus 1, that way it is estimator of x of n minus 1 given data up to n minus 1 plus again this is a white noise, this will be 0 and this will be 0. Therefore, we can further write that y cap, that prediction y cap n given n minus 1, that is also equal to a times x hat n minus 1 given data up to n minus 1. That way this is the estimator of the signal at instant n minus 1. Now, we will define the innovation like this: y tilde n is equal to yn minus y hat n given n minus 1. So, that way this is equal to yn minus e cap yn given y0, y1 up to yn minus 1. So, that prediction error is the innovation sequence. Similarly, suppose for any m less than n, we can consider y tilde m will be equal to ym minus summation e hat of ym given y0, y1 up to ym minus 1. So, this is the mth order predictor error. Now, because m is less than n, we can show that e of y tilde n into yj is equal to 0, j is equal to 0, 1 up to n minus 1, because error is orthogonal to data. So, all past data it will be orthogonal. Similarly, y tilde n will be orthogonal to yj because it is up to n minus 1. So, if we take some m which is less than n, then also this relationship will be true. Therefore, e of y tilde n into yj will be equal to 0, j is equal to 0, 1 up to m. Now, this yj, we are considering m yj's and their linear combination is y tilde m. Therefore, e of y tilde n into y tilde m will be equal to 0. What does it mean? This y tilde n and y tilde m are orthogonal. We can establish the same result by considering m greater than n also. Thus, y tilde n is an orthogonal sequence. Furthermore, e of y tilde n is equal to 0 because all signal we are considering 0 mean only. Therefore, this yn process is a white noise process which is obtained by linear filtering yn, because the generation mechanism is through linear prediction. Y tilde n is the innovation of yn, because after linear operation we are getting this y tilde n which contains the same information as the original sequence. Y tilde n is the innovation of yn and contains the same information as the original sequence. So, this innovation sequence is obtained by passing yn through a linear filter. Now, let us see the LMMSE estimation based on the innovation sequence. LMMSE estimation of xn based on y0, y1 up to yn is the same as the estimation based on the innovation sequence y tilde 0, y tilde 1 up to y tilde n. Thus, we can write the estimator x hat n given n as summation ki y tilde I going from 0 to n, where ki is called the Kalman gain. We will see later on why it is called Kalman gain, and can be obtained by using the orthogonality relationship. These coefficients can be obtained by using the orthogonality relationship, and this is the relationship we get. Kj n is equal to e of xn into y tilde j divided by e of y tilde square j for j equal to 0 up to n. We will see how this relation can be obtained, because error is orthogonal to data. Therefore, e of xn minus summation ki, that is nth instant, into y tilde I going from 0 to n into, this is the error and data is y tilde j, that must be equal to 0 for j is equal to 0, 1 up to n. And this implies that e of xn into y tilde j minus, now because this y I sequence is orthogonal, there will be only one term, that is kj n into e of y tilde square I. So, that must be equal to y tilde square j, that must be equal to 0, from which we will get kn is equal to, that is kj n is equal to e of x n into y tilde j divided by e of y tilde j whole square, like this. So, this is the relationship. So, now let us see how to get the recursive relation for the Kalman gain kj n. First write x at n minus 1 given data up to n minus 1 is given by this relationship, summation k I n minus 1 I going from 0 to n minus 1 y tilde I. And by the same manner we can find k j n minus 1, that will be equal to e of x n minus 1 into y tilde j divided by e of y tilde square j. This is for j equal to 0, 1 up to n minus 1, because we are considering the estimator at instant n minus 1. Now, I know that x of n minus 1 is equal to x n minus w n divided by a. From the model, x n is equal to a x n minus 1 plus w n. We can write x of n minus 1 is equal to x n minus w n divided by a. So, we will get this relationship k j n minus 1 is equal to e of x n minus w n into y tilde j divided by a times e of y tilde square j. Now, w n is independent of y tilde j, because this involved data up to n minus 1, j going from 0 to n minus 1, but w n is the noise at instant n, therefore, it is uncorrelated with all previous data, therefore, this term will become 0. So, therefore, we will only have e of x n into y tilde j divided by a e of y tilde square j. So, this is the expression. Now, we know that e of x n into y tilde j divided by a times e of y tilde square j, that is k j n, that we derived here. So, that way k j n will be equal to a times k j n minus 1 for j is equal to 0 up to n minus 1. So, this is the relationship between the Kalman gain at different instant. Now, let us see how we can get the recursion for the estimator. We have x hat n given n, that is the estimator, is equal to summation k I n into y tilde I going from 0 to n, and this is equal to summation k I n y tilde I going from 0 to n minus 1 plus k n n into y tilde n. So, that we are taking the last term out. Now, we can substitute this k I n is equal to a times k I n minus 1. So, that this relationship k j n is equal to a times k j n minus 1. Therefore, we will get this is here, from here we will get a times summation k I n minus 1 into y tilde I going from 0 to n minus 1 plus k n n times y tilde n. And we know that this is the estimator at instant n minus 1. So, therefore, this will be a times x hat n minus 1 given n minus 1 plus k n n into yn minus that prediction error is given by this E cap, that is the LMMSE estimator of yn from y0, y1 up to yn minus 1. And this we have already observed that this is equal to A times x at n minus 1 given n minus 1, that we have derived earlier. So, that way this x cap n given n, that is the estimator at instant n, is equal to A times the estimator at instant n minus 1 plus kn n times yn minus A into x at n minus 1 given n minus 1. So, this is the relationship we obtain, that is current estimator is related to the previous estimator. And if we take out this x at n minus 1 given n minus 1 here, so we can write here 1 minus kn n into A times x at n minus 1 given n minus 1 plus kn times yn. So, that way this is the recursive relationship. We see that this part is related to previous estimator and this is the part which is obtained from the current data. So, current data yn is multiplied by the Kalman gain, that is kn n. So, previous estimator weighted by this number and then plus this current data weighted by this number, then we will get the current estimator. So, this is the relationship, that is current estimator is either we can write like this, A times x at n minus 1 given n minus 1 previous estimator plus Kalman gain times the estimation, that prediction error. This is the prediction error. This part is prediction error. This part is prediction error. And that we can write in terms of data itself, that is 1 minus kn n into A times x at n minus 1 given n minus 1 plus kn n times yn. So, that Kalman gain is weighing the data. So, that way we see the importance of Kalman gain in this estimation. Thus, we have this relationship which we described earlier, that the current estimator is a linear combination of past estimator and current data. So, we have a filter structure now, that is current estimator, that is filter output is an times previous filter output plus kn times yn, or current estimator, that is filter output is equal to A times x at n minus 1 given n minus 1. This is the delayed version of the filtered output plus kn n times, that is Kalman gain multiplies yn minus A x at n minus 1 given n minus 1. This is the prediction error. So, that way we have this structure. Suppose this is my filter output is here and this is yn. So, the filter output will be delayed multiplied by A, and then this will be subtracted from yn, and that will be scaled by kn n, and then added to the delayed version of the estimator, that past estimator, that is x at n minus 1 given n minus 1 multiplied by A. These two will be added and then we will get the current estimation. So, this is the filter structure for the scalar Kalman filter. Let us see estimation of kn n. We have the estimator kj n is equal to E of x n into y tilde j divided by E of y tilde j square that we have obtained earlier. Therefore, Kn n will be equal to E of x n into y tilde n divided by E of y tilde square n. Now, this y tilde n we can write, that is observation x n plus v n minus the prediction. So, prediction is x at n given n minus 1. So, that way k n n will be E of x n into x n plus v n minus x at n given n minus 1. This x n and v n are independent. So, v n will not be there. So, we can simply write this is equal to E of x n into x n minus x at n given n minus 1. So, this is the relationship we get. Now, this is the expression for mean square prediction error, because we can write here x n minus x at n given n minus 1. Then also this part is orthogonal to this error part, therefore, the result will be same. So, instead of this expression now we can write this as E of x n minus x at n given n minus 1 into x n minus x at n given n minus 1. So, this is the result we got because of the relationship error is orthogonal to data, this part is error, and this estimator is a linear combination of data. Therefore, this error will be orthogonal to this. Therefore, what we obtain is that is k n n is equal to E of x n minus x at n given n minus 1 whole square. So, this is one term. In the denominator, we have E of y n minus x at n given n minus 1 whole square. Similarly, we can write y n is equal to x n plus v n and minus this quantity. So, that way denominator will be E of x n plus v n minus x at n given n minus 1 whole square. Now, after taking the expectation, we will have E of this part we can take together, E of x n minus x at n given n minus 1 whole square, and then E of v square n will be there plus twice E of x n minus x at n given n minus 1 into v n. So, that way we are expanding this expression. Now, we observe that this v n is the noise which is orthogonal to x n, and this x hat n given n minus 1, these are linear combination of previous data. Therefore, v n will be orthogonal to this factor also. Therefore, this term will become 0. So, what we will have therefore, in the denominator we will have E of x n minus x hat n given n minus 1 whole square plus E of v square n, that is the denominator. And this term, now we will denote this term by p of n given n minus 1. This is the mean square prediction error. You see, this is x n and this part is the prediction based on data up to n minus 1. That way it is mean square prediction error. Denominator also, this is mean square prediction error, same mean square prediction error plus E of v square n is sigma v square. Therefore, what we get is that Kalman gain at instant n is equal to p of n given n minus 1, that is mean square prediction error based on data up to n minus 1 divided by mean square prediction error plus sigma v square. So, this is one relation which we will be using to determine the Kalman gain. We need the previous mean square prediction error and the variance of the noise. Let us find the mean square prediction error p of n given n minus 1, that is equal to E of x n minus x at n given n minus 1 whole square. Now, according to the signal model, x n is equal to a x n minus 1 plus w n, and this x at n given n minus 1 is equal to a times x at n minus 1 given n minus 1, that is the estimator at n minus 1 multiplied by a. Therefore, we can write P of n given n minus 1 is equal to E of a x n minus 1 plus w n minus a x at n minus 1 given n minus 1 whole square. Now, this a we can take common, and there will be x n minus 1 minus x at n minus 1 given n minus 1. So, that way we can write a square times E of x of n minus 1 minus x at n minus 1 given n minus 1 whole square, that is the first term. Then w n, so E of w square n. Then there will be cross terms, 2 times a into E of this w n into x of n minus 1 minus x at n minus 1 given n minus 1. So, that way 2a into E of w n into x of n minus 1 minus x at n minus 1 given n minus 1. Now, this first term, it is the mean square estimation error at instant n minus 1. Therefore, this is P of n minus 1 given n minus 1, and E of w square n is equal to sigma w square. Now, let us examine this expression. So, if we consider the signal model, x n is equal to a times x of n minus 1 plus w n, and this w n is independent of x n minus 1 or x n minus 2, etc. So, that way w n will be independent of all past values of x n. Similarly, w n will be independent of all past values of data. So, therefore, E of w n into x of n minus 1 minus x at n minus 1 given n minus 1. Now, w n is independent of x n minus 1, this term will be equal to 0. Now, this estimator is a linear combination of past data only, it is a function of past data only. Therefore, this w n will be independent of this factor also. So, this is a function of y n minus 1, y n minus 2, etc. So, that way this will be also independent of w n. So, this part will contribute 0 therefore. Therefore, we will have P of n given n minus 1 is equal to a square times P of n minus 1 given n minus 1 plus sigma w square. So, this is the one recursive expression for mean square prediction error. Now, let us examine P of n given n, mean square estimation error. This is equal to E of x n minus x at n given n whole square. Now, writing x at n given n. So, this is we write in terms of that Kalman filter expression, that is equal to that prediction part x at n given n minus 1 plus that Kalman gain multiplied by that innovation y n minus x at n given n minus 1. So, we write like this. Therefore, E of x n minus x at n given n whole square can be written like this. Now, we will combine this part. So, x n minus x at n given n minus 1 whole square, one term will be there, plus kn n whole square into E of yn minus x at n given n minus 1 whole square. So, this part minus now twice a b term will come. So, minus twice kn n into E of x n minus x at n given n minus 1 into this part yn minus x at n given n minus 1. Now, obviously, this part is the mean square prediction error p of n given n minus 1, and this term will be E of yn is equal to x n plus v n minus x at n given n minus 1 whole square, that is equal to E of x n minus x at n given n minus 1 whole square, one term, then plus E of v square n plus twice E of v n into x n minus x at n given n minus 1. Now, this part v n is independent of x n and v n is independent of all past data. So, that way v n is independent of x at n given n minus 1 also. Therefore, this part will result in 0. So, what we will have is this is mean square prediction error, and this is sigma v square. So, we can write it as k n whole square into p of n given n minus 1 plus sigma v square. Now, we will examine this term twice k n into E of x n minus x at n given n minus 1 into y n minus x at n given n minus 1, and here this y n we can write as x n plus v n. So, what we will have is that E of x n minus x at n given n minus 1 into x n plus v n minus x at n given n minus 1. Now, this v n part will be independent of this x n and x at n given n minus 1. So, contribution of v n will be 0. Therefore, we will simply have E of x n minus x at n given n minus 1 into x n minus x at n given n minus 1. So, that way it will be E of x n minus x at n given n minus 1 whole square, which is p of n given n minus 1. So, that way this expression will be equal to p of n given n minus 1. So, we will have this quantity p of n given n minus 1 plus k n whole square into p of n given n minus 1 plus sigma v square minus twice k n into p of n given n minus 1. Now, we examine this expression. So, k n is equal to p of n given n minus 1 divided by p of n given n minus 1 plus sigma v square. From this relationship, we can get that k n into p of n given n minus 1 plus sigma v square, that must be equal to p of n given n minus 1. So, that way here we will write there are k n square is there, 1 k n will keep, and into p n given n minus 1 plus sigma v square. So, this entire expression will be simply equal to p of n given n minus 1, because this term we are writing as k n into k n into these things. So, that term will be simply equal to P of n given n minus 1. Therefore, we have P of n given n minus 1 plus k n into P of n given n minus 1 minus 2 k n into P of n given n minus 1. So, 1 P n given n minus 1 will get cancelled. So, we will have only one term here. Therefore, this will be P of n given n minus 1 minus k n into P of n given n minus 1, and this we can write like this. 1 minus k n into P n given n minus 1. Therefore, mean square estimation error can be expressed in terms of mean square prediction error by this relationship. That is, mean square estimation error is equal to 1 minus Kalman gain into mean square prediction error. So, we have this relationship now, that is the update equation for P of n given n minus 1 and P of n given n, and also we have examined that relationship for k and n, that is Kalman gain. So, all these relations will be used now in the algorithmic form. We will now describe the scalar Kalman filter algorithm. Here given the model parameters A, that is signal model is x n is equal to A x n minus 1 plus W n. So, A is given, then this for noise, this is a 0 mean white noise and its variance sigma W square is also given, and the similarly observation model is y n is equal to x n plus V n. So, V n, that is observation noise, is given to be 0 mean and variance sigma V square. So, these are given. We have to initialize the estimator. So, that way x hat minus 1 given minus 1 is equal to 0, because we do not use any estimated value. So, that way it will be 0, and under that situation, that is mean square prediction error, P of minus 1 given minus 1 will be equal to sigma x square is the variance of the signal, and we can use any positive number here. We start with n is equal to 0. Now, first step will be calculate the mean square prediction error. That formula we know, P of n given n minus 1 is equal to A square times P of n minus 1 given n minus 1, that is the estimation error of the previous step, plus sigma W square. Once this mean square prediction error is found out or calculated, we can calculate the Kalman gain, that is given by k n is equal to P of n given n minus 1, that is given here, divided by P of n given n minus 1 plus sigma V square. So, we will determine the Kalman gain. Now, we will take the input y n. Now, we can estimate x at n given n by this relationship, that is x at n given n is equal to A times x at n minus 1 given n minus 1, that is the estimator at instant n minus 1, which is multiplied by A here, plus Kalman gain k n into that innovation part is y n minus A times x at n minus 1 given n minus 1. So, this is the innovation, this is multiplied by the Kalman gain and added to the predicted value. Now, we will update the MS estimation error, that is P of n given n is equal to 1 minus k n, that is Kalman gain, into P of n given n minus 1 mean square prediction error, because this value is found out here, that will be used to update the mean square error, and then we will have n is equal to n plus 1 and we will go to this step. We will again calculate the mean square prediction error using this relationship. In that way this Kalman filter will go on. Here we have taken constant A, but to tackle non-stationarity we can take A as an as a function of n. In that case an will be also input to the algorithm at this stage. So, along with yn we have to give the value of an also. So, that way we have seen that Kalman filter recursively estimate the signal using a model, that is the AR1 model or Markov model, and under stationarity condition of this signal this algorithm will converge. Now, let us see this steady state behavior. At this steady state, let limit of p n given n, that is the mean square error, that is epsilon suppose, limit of p n given n minus 1, that is the mean square prediction error, that is equal to suppose p, and the Kalman gate limit of k n n as n tends to infinity is k. Then we will have the limiting form of the 3 Kalman filter equation. First one is, we know that p of given n minus 1 is equal to a square times p of n minus 1 given n minus 1 plus sigma w square, and as n tends to infinity this quantity will converge to p and this quantity will converge to epsilon. So, that way we will have, first one is p is equal to a square times epsilon plus sigma w square. So, from here p, that is the limit of this is p into a square, limit of this is epsilon plus sigma w square, that is the first equation. Then Kalman gain as n tends to infinity, that will be equal to k, and this one is by our definition this is p and this is also p plus sigma v square. So, that way second equation will be k is equal to p by p plus sigma v square. Now, third update equation p n given n. So, that way limit of this will be means epsilon, epsilon is equal to 1 minus k into p. So, that is the third equation, epsilon is equal to 1 minus k into p. These three equations can be solved to obtain the steady state gain and mean square errors. We will consider one example. Consider the signal yn is equal to xn plus vn, where vn is a Gaussian white noise with variance 1 and xn is equal to 0.8 x n minus 1 plus wn, where wn is a white noise with variance 0.36. The signal and noise are uncorrelated. Find the asymptotic expression for the Kalman filter output. So, here we have the signal model, that is xn is equal to 0.8 x n minus 1 plus wn, that is AR1 model with a is equal to 0.8, value of a is equal to 0.8. Then wn is a white noise with variance 0.36. So, sigma w square is equal to 0.36, and vn is also a white noise with variance sigma v square is equal to 1. So, these things are given. Now, the steady state equations will be, we have already established those equations here. So, first equation will be p is equal to a square epsilon plus sigma w square. So, at steady state that is, we have defined this quantity P is equal to, that is the steady state prediction error, is equal to A square times epsilon plus sigma W square. That is the first equation we got here. So, therefore, implies that P is equal to, A is now 0.8, so 0.64 into epsilon plus sigma W square is 0.36. That is equation 1. Now, second equation, we have the equation for Kalman gain, K is equal to P by P plus sigma V square, and this will be equal to P by P plus 1, because sigma V square is equal to 1. So, this is equation 2. And the third equation is mean square estimation error in terms of the mean square prediction error. So, that way third equation is epsilon is equal to 1 minus k into P. This k we have got here, this is the third equation. Now, we know k is equal to P by P plus sigma V square, that is P by P plus 1. So, that way this will be equal to 1 minus k is P by P plus 1 into P. Now, this will be simply 1 by P plus 1 into P. So, this is simply equal to P by P plus 1. So, epsilon, this is mean square estimation error, is equal to P by P plus 1. Now, this if we substitute here, so substituting this value in equation 1, we will get P is equal to 0.64 into P by P plus 1 plus 0.36. So, multiplying by P plus 1, what we will have is P square into P will be equal to 0.64 P plus 0.36 P plus 0.36. Therefore, this P and 0.64 P plus 0.36 P, that will be P only. So, this P and this P will get cancelled. So, we will get P is equal to square root of this, it is a positive quantity, therefore, this will be P is equal to 0.6. And also we have found out P, therefore, K will be equal to, implies that K is equal to P by P plus 1. So, this will be 0.6 by 1.6, 1 plus 0.6. So, that way 0.375. So, we have found out the Kalman gain and we have found out value of P. So, once we have the Kalman gain, now that signal update equation will be now x at n, that is we have to find out the asymptotic expression for the Kalman filter output, that is x at n given n, that is equal to that predicted value first is predicted, that is A is 0.8 x hat of n minus 1 given n minus 1, that this is the predicted value, plus Kalman gain is 0.375 into that innovation part is y n minus 0.8 into x at n minus 1 given n minus 1, and we can bring this here. So, that way this part we can combine. If we combine this is 0.8, this one will be 0.8, 0.375 here into 0.8, and both if I add I will get 0.5 here, 0.5 into x at n minus 1 given n minus 1 plus 0.375 into yn. So, this is the asymptotic equation for the Kalman filter output. That estimator is given by this expression. This is the 0.5 times the previous value of the estimator plus 0.375 into current data. Let us summarize the lecture. The scalar Kalman filter uses the first order air signal model. It is also known as Markov model. Xn is equal to A times Xn minus 1 plus Wn, and under non-stationarity condition this A will be replaced by An. So, under non-stationary condition, condition Xn will be equal to An times x of n minus 1 plus Wn. The observed data is given by Yn is equal to Xn plus Vn, where Vn is independent of Xn and Vn is independent of this Wn. We derive the Kalman filter based on the innovation representation of the data, that is y tilde n is equal to Yn minus E hat, that is the linear mean square error estimator, E hat of Yn given y0, y1 up to yn minus 1. And using the model, this part we showed that this is same as A times x at n minus 1 given n minus 1. The Kalman estimator is given by x at n given n is equal to A times x at n minus 1 given n minus 1, that is estimator at previous instant, multiplied by the Kalman gain kn n into, that is this part is the innovation, yn minus A times x at n minus 1 given n minus 1. This is the Kalman filter recursion, and this we presented in a block diagram like this. This is the yn data and this is the output x at n given n minus 1, that will be delayed by 1 unit z to the power minus 1 and then multiplied by A. So, that way we will get the prediction A times x at n minus 1 given n minus 1, that will be subtracted from yn and we will get the innovation. This one is y tilde n, and this y tilde n is multiplied by Kalman gain and then added with the predicted value. This is the predicted value x at n given n minus 1. This is the predicted value plus this is the corrected value kn times yn. So, that will give us the estimator x at n given n. So, we established the following Kalman filter steps. First one is calculate the mean square prediction error, that is P of n given n minus 1 is equal to A square times P of n minus 1 given n minus 1 plus sigma w square. So, mean square prediction error is equal to A square times mean square estimation error at the previous instant plus sigma w square. Then we will determine the Kalman gain on the basis of this P of n given n minus 1. So, this is the expression kn n is equal to P of n given n minus 1 divided by P of n given n minus 1 plus sigma v square. Now, we will estimate the signal x at n given n is equal to A times x at n minus 1 given n minus 1 plus kn n times yn minus A times x at n minus 1 given n minus 1. So, this is the Kalman recursion. Then we will update the MS estimation error P of n given n is equal to 1 minus k n n into P of n given n minus 1. So, this is the scalar Kalman filter and it explains the theory of Kalman filter very well. Next we will see how we can extend it to vector Kalman filter. Thank you.